Okay, so now we're going to be discussing about Kirchhoff's second law, or the Kirchhoff's current law. Now, this law is based on the conservation of charge. Similar to the conservation of energy, where one form of energy, when used, becomes another form of energy, conservation of charge states that charges don't disappear, they redistribute. So, if I have a charge like so, and then I allowed them to touch, then they might be electrically neutral now. So this is a symbol for neutral. There's no charge. Or maybe perhaps I have a have two conducting plates, for example, and I ran an electric field through them. Well, there's going to be a culmination of charges here and a culmination of charges here. That So we can see that for an electrically neutral plate, when we apply an electric potential or electric field, it redistributes the charges, but it doesn't take away the charges, or it doesn't make the charges disappear. That's the same idea with Kirchhoff's current law, where any kind of node and any that a current enters, or the sum of all currents entering going the sum of all currents in a node should be equal to zero. So what does Kirchhoff's current law say? So at a node, sum of all currents is equal to zero. Similarly to what we discussed with KVL, or Kirchhoff's voltage law, this might be confusing. So sometimes if you really need to kind of explicitly understand it, it is much better that we kind of state what it really is. So the sum of all currents entering should be equal to the sum of all currents leaving. Entering and leaving what? A node. So a node. So when you have, and the way we model a node is with a dot or with lines. If we draw a bunch of lines entering into the node, we indicate it by an arrow, either going to the node or away from the node. If it happens that they go into the node, then we call that current entering the node. Otherwise, if it's going away, it's leaving the node. And this is very useful as another general circuit analysis technique to model maybe equations using current instead of voltage. The other use case, and I should have discussed with KVL, is later on with shortcuts that are on these general circuit analysis. The reason why we don't want to use these general circuit analysis techniques all the time is because they would be very tedious. So that's the idea. Okay. And that's just our main discussion about KVL, and in this case, we wrapped it up with KCL. Both of these will guide us through all the different shortcuts, and hopefully it'll help you understand a little more about what they mean. Okay, thank you.